Hello, everyone, and welcome to another wonderful day of chemistry. So today, now that we've built up our series of equations that describe how our thermodynamic properties change, we're really going to dive in looking at our Gibbs free energy, which, as you may remember, for isobaric systems, so the ones we care about, this is really going to tell us about how favorable a given state or a given form of a molecule is. So a good place in trying to understand the stability of a system is going to be looking at the fundamental equation of thermodynamics for free energy. So again, this tells us that the free energy changes as a function of pressure and temperature. So we want to figure out how the stability of something changes. We can look at how it changes with respect to these two variables. Now let's go ahead and take these one by one. So if we start with the change in pressure, what we find is that uh, the change in favorability changes isothermally with pressure as a function of volume. What this means is that as pressure goes up, so will the Gibbs, because these are going to be positively correlated. And again, you can also look at this same way. I increase the pressure, I increase the Gibbs, I make the system less favorable. But especially if we're looking at states of matter, this gets really fun because different states of matter have different volumes. Or if we want to look at this in terms of size intensive properties, we can relate this as molar Gibbs and molar volume. Now, when we do this, what we find is if I'm going to increase the pressure, every I'm going to destabilize all three phases of matter, but I'm going to destabilize the solid much less than the liquid, and both of these much less than a gas, because a gas is going to be much more pressure sensitive because it is such a lower density. But also notice that for liquid and solid, these are going to be relatively straight lines because the molar volume is going to be relatively fixed. But gas, which has its nice ideal gas law pressure dependency, is going to be much more responsive as we have to actually worry about the full differential. So again, these are some major ideas that we should keep an eye out for, and we'll focus a little bit more in this next lecture. However, for the remainder of this one, we're going to really look at this second one, which is looking at how the favorability changes as a function of temperature. Now note here we have a negative relationship. That means that as the temperature increases, the system becomes more favorable. And this is going to be true for everybody. But notice it's going to be more favorable for systems with higher entropies. Now again, if we're looking at the same things in terms of different states of matter, what we're going to find is a gas is much more disordered and has a much higher entropy. So while inherently enthalpy does not like gases, entropy does. And so the higher the temperature, the more we stabilize this gas. And then liquids are going to have a little higher entropy, a little bit more disordered than solids. And so they'll actually respond to the temperature a little bit more. And solids are going to have a very low stabilization with temperature because their inherent entropy is so much lower than the other two. Now, we're going to specifically look at this relationship in between the stability of solids, liquids, and gases in great detail next chapter, because this is going to be the major feature of how we predict when phase changes occur, because that's going to occur when these lines cross and we switch what the most stable phase is. Today, we're just going to be looking a little bit more detail of how we can go ahead and predict the shape of these lines. Now, to do so, we're going to go ahead and start with this differential. And we're going to try and oftentimes when we're looking at these relationships, we want to avoid directly using entropy because entropy can, again, have some temperature variations and is a little harder to work with. So instead, we're often going to replace that entropy relationship with a relationship in terms of Gibbs and enthalpy. So we can replace that entropy term, rearrange it, and find that this negative entropy is going to be the same as the difference in between Gibbs, enthalpy, and temperature. So I can go ahead and substitute this ratio in for uh, the temperature dependence of Gibbs. Now, this actually shows a couple of interesting things that we don't get from this first expression. First, note that the change in Gibbs with respect to temperature is dependent upon the Gibbs energy itself. So again, this is going to cause some little interesting nuance. But more importantly is we also have this second order temperature dependence, because notice the change in Gibbs with respect to temperature depends on the temperature as well. So this makes working with the change in Gibbs with temperature very tricky because it relies both on the Gibbs and the temperature. So again, this can be a little bit nuanced, but it is also worth noting that oftentimes we're not interested in how the Gibbs changes with temperature. When we're trying to really evaluate the stability of something, it's worth noting a lot of our equations are going to depend on the entropy of the universe, not the Gibbs, because this is the property that really matters. So that means it's often useful to try and figure out the temperature dependency of this entropy of the universe term, which is the same as Gibbs over temperature. So let's go ahead and look at how this changes with respect to temperature. Now, when we do this, we can go ahead and use our product rule and find that we can do this by first leaving the 1 over t constant and then taking the derivative of Gibbs with respect to temperature, which, hey, congratulations. We now know this as we got this previously. Now, in the second one, we're going to pull the Gibbs energy out and then look at the change in temperature of inverse temperature over temperature. Well, in this case, we can insert both of these terms. So again, the change in Gibbs with respect to temperature is the Gibbs minus enthalpy over the temperature. And the derivative of 1 over temperature is just going to be negative 1 over temperature squared. Now notice we have a lot of these same terms showing up. So what we're going to do is try and simplify this out by first distributing the prefactors. So this gives us Gibbs over temperature squared minus enthalpy over temperature squared minus Gibbs over temperature squared. Now notice when we do this, we find that we have some canceling terms. And what we're left with is that the dependency of the universal entropy with temperature is based not on the Gibbs or the entropy, but more on the enthalpy of the system. And this is the real reason we want to look at the change in Gibbs with temperature in terms of the enthalpy. Now, this is actually fairly cool, and it's known as the Gibbs-Helmholtz relationship. And what it tells us is that when we're looking at how the favorability of a reaction or a phase changes with respect to temperature, what we're really going to be looking at is the enthalpy. And so again, the higher the enthalpy, the more favorable the system gets with temperature. And by more favorable, so the more positive the enthalpy, so again, the more endothermic the reaction is, the less favorable it will end up being. So this ends up bringing us to the temperature dependence. Next time, we're going to really dive into the pressure dependence. Until then, take care.